Right, folks, so this is the Le Châtelier's principle, okay? So this is what I want to talk to you about today. So this is an important principle. It helps us to understand reactions which are reversible. So let's look at a hypothetical equation, right? Let's say we have 3a plus, let's say, b, reversible, and then let's say 2c and d, okay? Now, let's say, I'm going to just move this a little bit here. Let's say the forward reaction is negative x, okay, kilojoule per mole. If the forward reaction is negative, then the reverse reaction delta H is going to be positive x kilojoules per mole, okay? So kilojoule per mole, so just put a kilojoule per mole. So basically what do we know? The forward reaction is exothermic, that means it is producing heat. The reverse reaction is endothermic, that means it's absorbing heat. So this is producing heat and this is absorbing heat, okay? Another way of looking at it is this is heating up system or surrounding. This is cooling down system. That means it's taking heat away from everything, taking heat away, so you feel cool, right? If something is absorbing heat from the room, you will start feeling cooler. That's basically what it is. All right, and another thing I want to highlight here to you is here we have 3 plus 1. So here we have 4 particles. And at the front here, 2 plus 1, we have 3 particles. Okay, so if we go on the reverse side, we are producing more particles. And if we go forward, we are producing less particles. Okay, going reverse, we are producing more particles. Going reverse, we are producing less particles. All right, so this is what you can see from this equation that I've given you. Okay, so what does the Le Châtelier's principle say, or the LCP? What does it say? It basically says when a change is made to a system or a reaction, a reaction which is at equilibrium, okay, when a change is made to a reaction which is at equilibrium, it's at equilibrium, the system or the reaction, okay, will try to overcome the effects of the change, something along these lines, the effects of the change. So it's like, for example, okay, now the system is at equilibrium, you introduce a change, you make a change, so the reaction will try to overcome the effects of the change. For example, in just very simple terms, if you try to increase the temperature of a reaction, what the reaction will try to do is reaction will try to reduce the temperature. So it will do the opposite. And then if you try to if you decide to reduce the temperature of the reaction, okay, the reaction will try to increase the temperature. So that's what I mean. So it will do the opposite of what you have done. Okay, it will do the opposite of what you have done. All right, so let's say for this particular reaction, this reaction that I've written here for you, okay, so let's say we decide to okay, let's say the first thing that we want to do is temperature. Okay, we want to talk about temperature. Okay, let's talk about temperature, the first thing we want to talk about. Okay, so for this particular reaction, okay, this reaction here, so the forward reaction is exothermic. So what we can do is, let's say we increase the temperature of the reaction. So the reaction is taking place in a container. So let's say there's a container here. Okay, this is where the reaction is taking place. A plus B and then C and D is being produced. So what we are going to do now is we have two options. Option number 1, we increase the temperature. Okay, we increase the temperature. Option number 2, we decrease the temperature. So the two things happening here, we increase the temperature or we decrease the temperature. So when we increase the temperature, these are the things that will happen. First of all, what will happen is both rates will increase. Both rates will increase. Please remember, whenever we increase temperature, rates of reactions always increase. Okay? But there's a but. But rate of the endothermic reaction will be higher than the exothermic reaction. Okay, so the rate of the endothermic, both will increase, but the rate of the endothermic will be higher than the exothermic. All right, so that's one thing that you need to know. Both rates will go up. But when we decrease the temperature, right? When we decrease the temperature, what will happen? Okay, let's say when we decrease the temperature. Okay, let's say we decrease the temperature. What is going to happen? So both rates will go down. Both rates will go down. Okay, but the rate of the exothermic will be higher than the endothermic. So when you decrease the temperature of something, it will try to increase its temperature and it will favor the side where it is producing heat. So both rates will go down. So you decrease the temperature, both rates will go down. The forward will decrease, the reverse will decrease, but the endothermic would decrease much more. Okay. Now another thing I want to tell you, and this is very important. Okay, important. Okay, important. All right. Only temperature change will change the K value. Okay, so let's say we look at this example here. Let's say just now I forgot to tell you. Okay, let's say for this particular reaction at 500 degrees Celsius, Kc is, let's say, 1000 units. Okay, let's say 1000. This will be m minus 1. Okay, m minus 1, that's the unit. Okay, let's say, so now the forward reaction is exothermic, right? So for this particular reaction that you're seeing currently, if for example, I take this reaction and I increase the temperature of this whole reaction mixture, I increase the temperature, what will happen is the reverse reaction will be favored. Reverse reaction will be favored. What is happening is the amount of the amount of reactants will increase, right? Because if you remember, the K for this particular equation that I'm showing you here is going to be C power of 2 D, and then it's going to be A power of 3 and then B. Okay, so you notice that the product is at the top, reactant is at the bottom, right? So currently this value was supposedly 1000. Okay, it was supposedly 1000. So now if I increase the temperature of this system, it's going to favor the reverse reaction. So I'm going to get more reactants. So what is going to happen is the denominator is going to increase. So what is going to happen is the K value will decrease. That means it will become less than 1000. Okay, get it? And for the same reaction, if I decide to cool it down, I cool the reaction down, it will favor the side which is exothermic. That means forward reaction will be produced. More C and more D will be produced. So which means that the K value will increase for this reaction I'm showing you. So depending on which side is endo and exo for the reaction which is given to you. Okay. So please remember, only temperature will change the K value, nothing else. Anything else that you see after this will not change the K value. All right. Then the other one, simple one I'll talk to you about is catalyst. Now adding catalyst to a system at equilibrium has no effect on direction. Sorry, what am I? Direction. Okay, has no effect on direction, but allows both rates to increase. Both rates will increase equally. Both rates will increase equally. So equilibrium is achieved faster. Okay, equilibrium is achieved faster. That's all. That's the only effect that catalyst has. All right, that's the only effect that catalyst has. Now, let me just 3a, b, and 2c. Okay, let me just recopy this equation here again. 3a plus b, and then, oops, I keep forgetting, 2c and d. All right, 2c and d. Okay, now let's look at this equation again. Okay, all right. So now what we want to do is we want to look at something simple. We want to look at something simple. Let's say we add a, okay, to the reaction. So that means we add a. When we add a, what will happen is system, or maybe forget the word system, reaction, maybe I just sorry, okay, forward reaction will be favored to get rid of the extra a. Okay, so if we add a, or let's say we add b, we add a or we add b, the forward reaction will be favored to get rid of the extra a or the b. Okay, or same thing if we remove some c or d. Okay, we remove some c or d, then what is going to happen is the concentration of c or concentration of d will decrease, right? Okay, will decrease. So what will happen is, again, forward reaction will be favored, okay, will be favored to produce more c or d, right? So same thing here. So in this case, when we add a or b, right, what happens is the concentration of a or concentration of b in the reaction mixture increases. So the forward reaction will be favored to get rid of it. Same thing if I remove some c, if I remove some c again, or I remove some c or remove some d, the forward reaction is favored. But if I decide to remove some b or a, then the reverse reaction will be favored. Okay. All right, so that is the effects of adding or removing things now. All right. Now, the other thing I want to talk to you about is like, I want to talk to you about is changes in concentration. Okay, changes in concentration. So this was changes in concentration actually. Let's say you have a system which is a gas. Okay, let's say you have a system which is a gas. Okay, let's say the same reaction just now again, right? Let's look at the same reaction again. 3a plus b. Okay. 2c plus d. Okay, now let's say this reaction was aqueous. Okay, so this is a system which is aqueous. Okay, let's say this is the entire system inside of this. So there is a, and there's plus b, and then there is c and d. What we decide to do is we decide to dilute the system. Okay, dilute by adding more water. Okay, we dilute by adding more water. So what happens is when you add water, right, the system, the whole reaction mixture becomes dilute. Okay, so what happens is entire reaction mixture becomes dilute. Okay, entire reaction mixture becomes dilute. So what will happen now? System will favor the side which has a greater number of particles. Okay, greater number of particles. So if you look at here, right, so just now 3 plus 1 is 4, and this is 2 plus 3 is 2 plus 1 is 3. So you realize that in this particular case, the reverse reaction produces more particles. So in this particular example, in this example, in this example, the reverse reaction is favored. Okay, in this example, the reverse reaction is favored. So if we dilute it by adding more water, if you remove water, let's say you put it under the sun and you just boil it, remove water, what will happen is we are concentrating the system. So when we concentrate the system, the system will favor the side where there are lesser particles. That means when we remove water from the system, we are concentrating it, it will favor the forward reaction where there are less particles. Okay. Then same thing if we're talking about gases, right? Let's say 3A plus B and then 2C plus D. Okay. Now let's say this was gas, this was gas, this was gas, this was gas. Now for gases, what we can do is, let's say we have a container, right? Let's say we have a container here. So let's say inside here again is A plus B and then it is producing C plus D. All right. So there are two things that we can do to this mixture, right? We can increase pressure or we can decrease pressure for gases. How do we increase pressure? We increase pressure by what was that? We increase pressure by decreasing volume. Okay, by decreasing volume, and we decrease pressure by increasing volume. Usually that's what we do lah. Okay, it's something to do with Boyle's law, which later on we will learn about P equals to 1 over V. All right, doesn't matter. If we increase pressure, what is going to happen is a system will favor side with we're increasing pressure. That means, wow, you're feeling so much of pressure with lesser particles. Okay, that means in this case it is going to be, i.e., forward reaction. Okay, and then now what's happening here is you are decreasing pressure by increasing volume. So much of volume, so much of space. So what is going to happen is system will favor side with greater number of particles. And in this example it's going to be the reverse reaction. Okay, the reverse reaction, because it produces more particles. Here was 4 and here was 3. Okay, so this is what I mean. So basically what is happening is if we increase the pressure, we decrease the volume, it's going to favor the side where there are less particles. If we decrease the volume by increasing decrease the pressure by increasing the volume, then it's going to favor the side where there is more particles. All right, and one last thing I want to tell you here. You see, again, in these cases, right, in these cases where we are manipulating volume and all those kind of things, right, when we decrease volume or we increase pressure, what is happening is both rates go up. Okay, and in this case both rates go down, because increasing volume, right, increasing volume is the same as diluting. Whenever you dilute something, the rates will decrease. Okay, so in this case both rates will go up or go down depending on what we are doing. And again, same thing like just now, both rates will go up, but what rate of reaction producing more particles will be higher. Okay, so in this case both rates will go up, but rate of reaction producing lesser particles will be higher. Okay, all right, I think that's basically more or less what I did with you today. Okay, so I'll stop here and we are done.